Remember that? Yes? And
Are those the number problems?
yeah, these, oh, oops, I forgot to put page. Page, sorry, thank you. Page starts on page 385. Numbers 3, 5, and I was looking, I do have a homework solution video for this section, but I don't do all of these problems. I think I do number 3, number 5, and number 15. So just so you know, some of those aren't done. And I doubt I'll do them. I'll let you just, you know, I don't think I'm going to find the time to do it right now. So, okay, so shells, right? We started talking about that last class. I have a handout for you here today. Not a quiz, just a handout. What I did was I put together something that summarizes the methods that we have for finding volumes of solids of revolution. If you could pass these back. I don't intend on this being something you can use on the test. It's more of something that kind of puts everything in one place for you, so when you're studying, you have it. There you go. Oops. So let's go through this now. When I printed it, when I made it, it looked like it was going to print out real nice so you could see everything, but then I printed it and some things came out really small. So, okay, so look, when it comes to solids of revolution, what we want, we're kind of going to do a quick review here right now. When it comes to solids of revolution, there are two methods, all right? And the whole idea is we're going to take some region and we're going to wrap it around either the x-axis or some horizontal line, or we're going to take the region and wrap it around some vertical line. And we will never do anything other than vertical and horizontal, all right? Not in this class. So when it comes to washers, the main thing that kind of tips you off that you're going to need to use this method is the fact that the rectangle that you draw within your region is orthogonal, which meant perpendicular, right? Is perpendicular to the axis of rotation. So if we draw your little rectangle and your axis of rotation, if those are perpendicular, you want to use washers. Also, keep in mind that when you draw your rectangle, what you're looking for is that the function on the top of the rectangle would always stay the same as you move the rectangle from left to right. Like it's always the blue curve, then this would always be the green curve, right? As you move this left and right. Then that's a good rectangle to have, all right? If we do that, then the end of story kind of formula, and I tried to generalize it as much as I could, is that you're going to have pi integral from a to b, which is your limits on x, and then it's going to be your outer radius squared minus your inner radius squared dx. And remember, the outer radius and inner radius is always dependent upon your region and where the axis of rotation is. For this particular drawing, I put the axis of rotation down here, right? But it could have been up here, it could have been down here, it could have been the x-axis, right? So I couldn't give you a general formula. You have to kind of understand that you're always going to have to calculate this, yes? Okay. Now, the other way we could do washers is if our rectangle is horizontal and our axis of rotation is vertical, and it's basically the same story except everything's with respect to y instead of x, right? And the formula only changes are these two are now y values. This is dy, but we still have to measure an outer radius and inner radius. Okay, and then we start talking about shells, right? And that's where I want to pick up. That's going to be on the back side of this, but I'm actually going to skip that, and we're going to do an example first. All right, so let's do that. So let's take this first example here. Find volume of solid if region shown is rotated about, we're going to do a couple of these. Part A, the y-axis Part B, let's say x equals -3. Part C, x is equal to 6. Okay, so I'm going to draw you a region, and then we're going to rotate it around 3 different lines. So let's use this region here. One of these is going to be good. This is the curve y equals 4x minus x squared. And we're talking about the region right in here. All right? Okay, so let's do part A. So for part A, I'm going to wind up drawing this picture 3 times. All right, so let's just kind of get used to that idea. Here's my region. And my axis of rotation is actually the y-axis for part A, right? Which is this. So I'm trying to rotate this around that axis. Now, could we use washers? Or would we run into problems with washers? If I use washers, is my rectangle vertical or horizontal? If I use washers. It always has to be perpendicular to the axis of rotation, right? So if my axis of rotation is here, my rectangle would have to be drawn like this, if I'm going to use washers. Now, if I put a rectangle in here, let me go ahead and put it in here. If I did this, would that be a good rectangle or no? No, because the part of the rectangle on the right side, that curve, is actually the same curve as the one on the left side. So you would have to do something to maybe solve this for x, and then you would have like 2 functions because you'd have square roots. It would be complicated. Would you agree? Yes. I mean, could we do it? Maybe, yeah. But it would make more sense if we could have this rectangle be vertical. Because if it's vertical, then my top function and bottom function are always the same as I move this from left to right, right? So that's a nice convenient choice. Y'all agree? Okay, so now, from last class, what we tried to understand from this, and I know it was kind of towards the end of class, what I did was I drew the y-axis, I drew the rectangle over here, I drew my axis of rotation, which happens to be the y-axis again. So I'm drawing 3 things there. The y-axis, the axis of rotation, and the rectangle. And then go back and look at, I'm going to have to bring this up here. Normally I draw this below that, but if I wrap that rectangle around, I get this shape here. And this is where last class what we did was we came in here and we cut it and we laid it open and we came up with a formula for it, right? Okay, and if you look back in your notes, what we determined was that the volume of the entire thing wrapped would be 2 pi integral a to b. Anyone remember the next part? Well, that's what it says on the formula sheet, right? But in class I said it was x, okay? I said it was x because of the problem we were looking at. So what I want you to remember is that when we took this thing and we cut it open and laid it out, we had this little slab, didn't we? And the height of the slab was the top function minus the bottom function, right? So that was f minus g, this side. And then the thickness of this little slab was what? It was dx. It was the width of the little rectangle, which we've always said is, well, dx in this direction, right? So dx here. And then we had to figure out how long this thing was. And that we said was 2 pi times the radius. And the radius we meant was the radius of this shell, okay? And so we need the distance from here to here. Now you have to remember that's like infinitesimally thin. So we don't have to look at like a little outer inner radius. It's just the distance from the axis of rotation to the edge of this, okay? And when you look at that over here, that's this, isn't it? That's our radius. In this particular case, because the radius is the distance from the y-axis to the rectangle, that's just x. Okay? In another problem like part B, where's our axis of rotation going to be? It's going to be over here, right? So the distance from here to this is not going to be x anymore. All right? And we'll deal with that. All right? But the important thing is that in the formula that we'll look at in a second, you have in front of you, it's r, right? That's what I have written there, r. And then it's the f of x minus g of x dx. Okay, so that's our formula. Make sense or not? Is this making sense? Okay, so can we do this then? Are we ready to set up the formula for this? I mean, we can see that this right here from here to here is x, right? And we can see the top minus, what's the top minus the bottom here? What's this side? So what's our top function? That 4x minus x squared, right? And then minus what? What's the bottom function? Y equals 0, so that's 0 here. So I really do have f minus g there, but g is 0, so I don't have to really write it in there. So I think I'm ready to go straight to this now. As long as I know a and b. Do we know a and b? You can see it from the picture, can't you? 0 to 4. So the volume will be 2 pi integral 0 to 4 of the radius, which is x, times, in parentheses, well, the difference of these two, right? Which would be 4x minus x squared dx. And that's it. Of course, we could integrate this pretty easily. We just distribute the x through term by term, just do them, and then we'd be plugging things in, and that'd be it. We've done. Okay? So, I'm going to bring up the notes again. And let's just talk about shells. And then we'll do part B and C, okay? So for shells, it's hard to figure out what's marker and what's. Why did I do x?
Yeah, what was it? Where did the x come from for the x times 4x?
Okay, so let's get this clear, because I think this is the part that causes the most trouble. When we're doing Riemann sums, okay, if we have some function here, this is back when we were first starting Riemann sums, we were drawing rectangles, weren't we? Yes? And we were saying, look, we're gonna start drawing our rectangles at A, and we're gonna end at B. And what we did was we had when we did a bunch of rectangles, we had this jump that we had, right? Every jump here was dx, yes? It was our change in the x coordinate of the rectangle. So you can imagine that this rectangle has some x coordinate, doesn't it? As it moves from A to B, it has an x coordinate. Now, because the rectangle becomes super, super thin, we can look at that as being like a single point as opposed to like a left end point or a right end point. It's kind of gets smashed in between, and there's like one point. Does that make sense? But it is a measurement of the distance from the y axis to that rectangle. So that is an x, isn't it? Like if I told you to go out to this rectangle, you'd have to walk out a certain distance. And that value is x. It's a variable because we're allowing it to change. Yes? Does that make more sense?
Okay.
So that's why when I said, what's the radius? When we're wrapping this around like this and creating this shell, right? When we're doing that, the radius is distance from the axis of rotation to the edge of that sliver, right? So it's that distance. And in this particular problem, that's x.
Okay, so that's a radius.
That's the radius. But it's not always going to be x. That's what we're going to see in part B. It's going to change. Does that help clarify it?
Yes.
Anyone else have a question on that? What you can say is this. The distance from the y-axis to your rectangle is always x. That's always x, all right? But the distance from the axis of rotation to your rectangle may not always be x, all right? Okay, so this note says, look, if we have an axis of rotation that's vertical, right, and we have a region that looks like this where it's very convenient for us to use a vertical rectangle, then if we want to wrap this, we can't use washers, we have to use shells. So parallel to the axis of rotation, your rectangle. Then you wrap this around, you get this object. We went through this already. This would be f minus g, this is dx, and then this length is 2 pi r. 2 pi r is the circumference of a circle, yes?
So we're just putting the r inside of the integral, right?
Yes, r goes inside, the 2 pi comes out because it's constant. The r goes inside because r will be a function of x. Because it's going to move, right? This rectangle is going to move, so it's always dependent on x. So, yeah, there's my drawing of it again. So look at this right here. What I did is just brought this down, brought the y-axis down, brought the axis of rotation down. The distance from the y-axis to the rectangle is x always, but the radius, right, r, is this distance. So you might actually have to measure what this is, all right? And whatever r is, then you just plug it into the formula and you get 2 pi integral a to b, which is our variation on x. Top minus bottom, there's your radius dx. That okay?
So if that purple line were like -4, it'd be like
X plus 4.
x plus 4. Okay.
That's right. So part B and C, we're going to do this. Okay? All right, now, what if you have a region that looks like this? Look at these curves. These are functions of y, right? Not functions of x. What if we want to wrap this around something this way? We would not want to use washers, right? Because again, if you try and draw a vertical rectangle, your top and bottom functions are going to have problems right in here, right? You're going to have to switch it. You would have to change it, especially over here, right? You'd have an issue. So if you have functions of y up there and you want to go this way with them, it would make more sense to use a method that allows your rectangle to be parallel, right? So we would want to use shells. And it would go the same, this is the same setup, just the other direction. So here's my x-axis, here's my axis of rotation, here's my rectangle. When I wrap it, I get a shell that looks like this. This right here, f minus g. Remember, f is the function that's on the right side, g is the one that's on the left. So this is all very similar to what we've done. It's just our formula is changing. We have dy instead of dx. And then look at our radius now. Our radius is the distance from the axis of rotation to the rectangle. The distance from the x-axis to the rectangle is always y this time, because we're varying y. So our formula changes a little bit, right? Only difference is c to d, dy, everything else pretty much the same. All right, I'm going to go back to this example we were working on. Is this making sense or not? Okay, so we had the curve y equals 4x, no, I said 4x, I wrote 4. Okay, 4x minus x squared, and we were on part B where we wanted to rotate this around x is -3, right? So when I do my drawing here, here's my region, okay? My axis of rotation is here now, right? So if I'm doing that, are you seeing, is it easy for you to see how knowing what the region looks like and where your axis of rotation is, that will some way dictate which method you want to use, shells or washers? Okay, so this one obviously, shells would be good, right? Because my rectangle can easily be drawn here like this, as opposed to the horizontal rectangle, which would have problems, right? So I want to use shells. I need to determine my radius for this. So I'm going to bring my dotted axis of rotation down. Here's my y-axis. Here's my rectangle. I already know this distance, right? We've got that piece already. That's 4x minus x squared. We did that on the previous one, right? And so all I need now is the radius. I need the distance from here to there. That's r. But we just said that the distance from here to here is always what? X. And what's the distance from here to here? So we look at it as like an absolute value because it's a distance, right? So that measurement is 3 because this is -3, right? So that's 3. So my radius must be 3 plus x or x plus 3. It doesn't matter which way you do it. right? That's my radius. I didn't need the parentheses. And once you have that, that's it, right? You go right to the formula. So the volume will be 2 pi. So when we're using shells, it's 2 pi, right? When we're using washers, it's pi. Okay, integral, and then we've got 0 to 4. It's our change in x. It's going to go from 0 to 4. And then our radius, which is x plus 3, we need that in parentheses. And then times the f minus g, which was 4x minus x squared, then dx. That's it.
We don't find anything there's a 0, right?
Pardon? Yeah, because the g was 0, right? This is f minus g, but you just can't really see the g. Yeah, so like if there was, let's just say for the sake of saying it, if there were like another curve that did something like this, let's say they intersected at the same points, right? Then my rectangle would have come down like that. And then I would have needed to know what that is, and it would have been this minus whatever that other one, the red one was. So we would expand this out, like FOIL it out or whatever, and then term by term, and it'd be pretty straightforward. All right, part C. No questions? Part C, we have the axis of rotation is now x, what did I say, 5? 6, okay. And go with another picture. So you kind of got to know where things are as you draw it. So here's my region right in here. My axis of rotation is over here this time, right? My rectangle's in here. Going to be using shells. So if I redraw this down here, notice I have my y-axis here, I have my axis of rotation here, and my rectangle's in here. So I'm interested in R. R is going to be the distance from here to here, right? From axis of rotation to your rectangle. The things that we know are that the distance from here to here is x, right? And we know the distance from here all the way to here is never changing. That's always just 6, right? So as this moves, the radius changes, and that will always be what? 6 minus x. So it can't be x minus 6. It has to be 6 minus x. It's the total distance x, but then you take away whatever that distance is, and that will give you your radius. Everything else in the integral is the same, right? The rest of the whole setup is exactly the same. So the volume is 2 pi integral 0 to 4. My radius is different now, 6 minus x, but the actual f minus g is identical. Okay, so I'm going to put up here. These are the 3 problems we just did. Sorry, thought I had more room. Those are the 3 problems we just did, right? The only difference in these 3 problems is that, right? And that's just the radius changed depending on where my axis of rotation was, right? Everything else is identical. Okay, well, that's pretty much it. You'll feel okay with that, you think? Yeah. What? No? You're okay? Okay. All right, so when we're talking about what's going to happen on the test, all right, most likely what you're going to see on the test is a couple of problems like this. I give you some curves. You have to draw them correctly. You have to find their points of intersection. So I might give you a curve. Let's say I give you 2 curves like this. One hits there, one hits, or let's say they hit like that. Let's say I give you something like this, all right? So you have to come up with that drawing on your own first. So it's very important that you get that right, yes? Okay, so let's say you do this. You find out this is F, this is G. So here's your region. There's a couple things I could ask you. I could ask you for the area, right? So the area would just be integral A to B, right? Of the top minus the bottom, done, right? Okay, I could ask you to rotate this around the x-axis, which you would want to use which method? Washers, right? So that would be something like pi integral A to B, top function squared minus bottom function squared. Okay, that would be around the x-axis. Then I might ask you to rotate it around a line down here. So that would be like pi, and then you'd have to figure out what the outer edge is, right? So you'd have to figure that out, squared minus the inner edge squared, right? And then I give you a line up here to rotate it around. Washers again, figure out the radius, same story, yes? So I give you a region, ask you to wrap it around 3 different horizontal lines. Then I give you same region around the y-axis. So how would you do that one? Shells, right? How about around this? Shells. Around this. Shells, right? So that could be a problem on the test. I would expect that. Region, and then at least 6 rotations. Which you just have to do the formulas, right? Then I'm most likely going to give you something that looks like this. So now I give you, these are not functions of x now, right? These are functions of y. And so what you would probably want to do here, I should have done this earlier. Everything I did on that one, my rectangles were like that, right? Here you want this. So if I ask you to go around the x-axis, you're going to use shells, right? But everything's going to be dy instead of dx. And then I could go down here, right? You have to change your radius. Up here, you have to change your radius. Then when I ask you to go this way, right, around the y-axis here and here, you're going to use washers. Make sense? Okay. So that's what I would expect on the exam, which is, we're going to have it today. I've changed it. We're going to do it right now. Yeah, let's see. Oh, we're still a ways off. November 14th. All right, here we go. We are done with solids of revolution. All right, we're done with solids of revolution. We've done 7.2 and 7.3, but there's something else in 7.2 that's at the end of the section that I've skipped intentionally, and now we're going back to it. So we're still in 7.2 right now. All right, and I have a visual aid for you. I made this the other day. Pretty proud of it. It's pretty awesome. Yeah, look at this. Yeah, thank you. Yeah, I appreciate that. Yeah, it will be. It will be. Okay, so we've got 2 curves here, right? We've got these 2 curves, and we could talk about the area and all that junk, but we're gonna be changing gears. No longer are we thinking about revolving something around an axis. All right? I don't want you to think about that. I want you to just listen to what I'm about to tell you. All right, imagine if you could a solid, all right? So, this is kind of like a solid, right? This is a solid, 3-dimensional object. I'd like for you to imagine a solid sitting over here where the base of the solid, the bottom of it, is this region right here, okay? So that's the bottom of the solid I'm talking about. And then if we were to come in here with a knife, and if we were to make cuts into this solid, so imagine I've got that solid sitting right here, right? And it's got some top to it, and I'm going to try and describe that top to you right now, okay? So I'm going to take this solid, I'm going to take a knife, and I'm going to make a cut. Now this cut that I'm going to make through this solid, the cut I'm making is perpendicular to the x-axis. So I'm not cutting it like this or like this or like that. I'm cutting exactly straight perpendicular to the x-axis. When I make this cut, all right, so imagine I take like a really, really, really nice knife and I cut, and then I just move over just a little bit and I cut a little more, just like this little sliver, okay? And I take that little sliver out. What if I tell you that the sliver I got, that I cut out was an equilateral triangle, all right? Okay, it's an equilateral triangle. Now, equilateral means all sides the same length. But this length of this side right here is actually the distance from this function to this function. So when I made that cut over here, when I made that cut and took the little sliver here, I got this, right? Now, if I were to move my, here's all my stuff. I thought I had more than these. Oh well. If I were to move my cut over a little bit and cut again, I'm going to get another equilateral triangle, but this time the distance is from here to here instead of here to here because it's shorter, right? Shorter here, longer here. So now that's this. Yes? And then if I move almost to the center of this region and take a cut, I've got this equilateral triangle like that. So here's the technical way I guess we say this. Imagine a solid whose base is this region and perpendicular cross sections form equilateral triangles. Okay, we have a three-dimensional solid whose base is formed by this region. Perpendicular cross sections to the x-axis form equilateral triangles. Find the volume of that solid. So we want to find the volume of this solid. Now, it's hard to describe, like I can put all these together, right? You can kind of get an idea of maybe what this kind of looks like. Eh? Okay, maybe. Bless you. All right, so let's try this way. There's that stuff, you know, that graph laying on the, I've got it and I'm laying it kind of on the ground, right? And I'm going to take, we want to do equilateral triangles. So imagine now as I move this, y'all see my cuts are perpendicular to the x-axis. Do y'all agree? But if I look at it kind of from the side, I can see like a cross section. And those cross sections are forming equilateral triangles. And as I move my cut towards the edge, look how small they get, right? But as I go towards the center, they get bigger because the distance between the two functions is what's dictating the length of the side, right? So I go up here and it gets as big as it's going to get and then it starts getting smaller. If I were to put all of those together, you know, all those, then I would get some object, right? Some solid that would look like this, right? Do y'all see that? And if you come look at it from this direction, you can kind of see those triangles. I'll bring my cut back through the other side. There it is. So you see those triangles from the side. Got it? If we were actually given the equation of that curve and the equation of that curve, like these are two parabolas, if I were to give you those, the question is, can you then tell me the volume of this solid? All right? Do you understand what's going on? Okay, so let's start over.
So that's only like half, that's not like.
No, see, I'm not rotating.
Okay.
So let me rephrase the question again, or the statement about the solid. We have a solid whose base is the region bounded by these two curves. Cross sections perpendicular to the x-axis form equilateral triangles. Okay, find the volume of that solid. So there's no bottom to this for this particular one. Now, I used triangles, right? I said, let's do triangles. What if I told you instead that the region between these two solids, right, the region between these two curves is the base of a solid. And when I take cross sections that are perpendicular to the x-axis, I get semicircles, where the diameter is the distance between the two. So I'm talking like that. I have a full circle there. I shouldn't have a full circle there. It should be a semicircle. That should only be just the top half of that circle. I'm not quite sure why it's coming out that way. But you see, as I move through, I get smaller and smaller circles, and then bigger circles, and then when I go to the other side, small circles. If you put that all together, you get a solid. That solid is different than the one we just looked at before this, right, with the triangles? So the question would be, what's the volume of that solid? Understand?
Are those different functions in the last?
We're saying these are the same two curves, the red and the blue one. Yes?
So the one difference we need to know is the height of that base?
Yeah, we need to, well, it's going to be, we're going to need to know a little bit more than the height. You'll see as we put it together. Right now I'm just trying to get you to see what we're doing visually first. I could have done squares, right? Instead of triangles, what if I did squares? So you see how the squares would work? the distance from here to here would be the same. Now, it doesn't look like it, does it? Those don't look like squares. I must have my aspect ratio. I thought my aspect ratio was correct.
Did you write this?
I wrote that, yeah. Where the hell's my aspect ratio? I guess I never put an aspect ratio on this. It's a C-based language, but it's not exactly C. Hold on. Let me do this. Where am I? No, it's not aspect ratio. Let's see if this works. That look more like a square? Nah, when I moved it, it changed it, didn't it? Yeah, okay, so it came off initially, it did it, but yeah, I may not be able to, for some reason it's changing as I rotate it. Maybe, does that kind of look squarey to you? I don't know, whatever. You get the idea, right? These are squares. So if I were to put all these together, right, I would get a different solid. There's that solid, kind of cool looking, right? So what is the volume of that solid? And I could just, any geometric shape that I could think of that could somehow be a cross section we'd be able to hopefully find the volume. Yes, I will definitely have to let you know if it forms, triangles or squares or circles or something else, okay? So let's do a problem, all right? I just wanted to get you to see visually what we're trying to do, all right?
Yeah, there's a problem with it on my homework now.
Yep, yeah, you weren't supposed to do that. I thought I told y'all not to mess with that one, but
Sorry.
it's all right. Okay, so let's do this. Let's say that we have the region bounded by I guess we can go pretty simple here. We'll just go y equals x squared minus 2 and y equals x squared plus 2. No, negative x squared plus 2. So the region bounded by those two curves forms the base of a solid. Find the volume. I guess I should write find the volume. If cross sections perpendicular, I'm just going to write perp, is that okay? Perpendicular to the x-axis form, and we're going to do three things. We're going to do three different solids. So let's start with squares first, because I think squares is the easiest. Then let's do semicircles. Semicircle is a half circle, right? And then equilateral triangles. All right, now before I do this, my other class, we had to resolve something before we did it. I tried to do it without talking about this first, and we had some problems. So let's clarify something. Remember this. If you have a cylinder, right, and we want to know its volume, we all agreed that the volume of this would be pi r squared h, right, where the height of this was h, right? And then pi r squared is actually just what? It's the area of the base, or you could say of the top. It's either one, right? So this up here, this right here has an area, and that area was pi r squared. So this volume is the area of this surface times how deep it is, yes? Yes? Okay, so in general, if you have a three-dimensional object like this, if it has some weird surface on top, and then you just drop everything straight down, and you look at that surface, okay, so that surface, just give it some depth. Then if this is h, and this thing has an area, we don't know what it is in this case. Here we know it's pi r squared. But generally speaking, if this is just some weird object, weird region, then the volume of this would be that area, right, times the height. Can we agree on that? Okay, I need that to proceed. So any three-dimensional object we have, if we can find the area of one of the faces of it, and just imagine moving that face a certain distance, then the volume would just be that. Okay? So let's try this problem. Let's do the squares first. So I'm going to draw a picture for part A. You know, I'm going to get rid of this. For part A, let's start with the picture of the region. So it's going to go like this. That's going to be y equals the second one, right? So negative x squared plus 2. And then we have another curve that has the same x-intercepts, right? And that one's going to be y equals x squared minus 2. Where do they intersect one another? Is it 2? Is it 1?
So it's 1.
You'd have to set them equal to each other? Or you just find the x-intercepts of one of those? Root 2, negative root 2 is where they hit. Root 2, negative root 2. Right? Because if I plug in here, let's say in this one, if I plug in root 2 and I square it, I get 2. 2 minus 2 is 0. If I plug in root 2 here and square it, I get 2, and then negative 2 plus 2 is 0. So, that okay? I could trust that you could get that with enough time? Okay. All right, so there's the base of our solid, right? There's the base of our solid. If we take cross sections of this, so if we come in here and cut this, right? If we do some cut, and that cut is perpendicular to the x-axis, so I'm cutting like this, then if I do some little infinitesimal slice out of this, that's what it would look like from the top, right? That would be my little infinitesimal slice. That cross section, the cross section of that is going to be in what, square? Okay, so now I'm going to try and draw this picture in three-dimensional space. Now this, what I'm about to do here, took me a long time to get good at this, so I understand if you look at this and go, what? So let me show you how I like to draw in 3D. First thing I do is I draw what's called our z-axis, which is going to be our up and down. Then I'm going to draw the x and y-axis. And the way I do this is I'm going to draw an x, okay? I'm going to draw an x, but I'm going to squash the x down. Right, so watch. Oh, there we go. Okay, you see that x that's squashed down? So if you try and draw like a normal x, like that, it's not going to look right. It's going to look weird. Like that's hard to visualize as three-dimensional space. This one, do y'all see that that's like a better representation of almost like the corner of the room over there? Okay, then what I like to do is take this, call that my x-axis, call this my y-axis, and this is my z. So essentially what I've done is I've taken this picture right here, right? And we're kind of looking at it from this perspective like this, and we imagine like a z-axis coming out of this. Everyone see it? Okay.
You're like holding it flat, like.
Yeah, this is like the xy, we call it the xy plane, is actually the ground, and this is coming up out of the ground. Okay, got it? Sure?
What's
Now,
the trick for assigning the...
right-hand rule.
Yeah, how do you... So it's z and then x
how many of you have heard of the right-hand rule? Yeah? We haven't talked about it in here yet, have we? We did, right? I told you about that thing?
I just want to make sure.
Yeah.
Thumbs up.
It's the right hand rule. This hand, though. Use the right hand, not the left hand. Okay, so here we go. I need to draw that. So I know that on the y-axis I have this intercept right there, right? So that would be somewhere like over here, let's just say. And then on the x-axis I have an x-intercept here and here. So that would be like maybe here and over here, something like that. And then watch me draw this. This is very strange when you do this. Especially this one right here. It's not very symmetric looking. But when you draw it, I still don't like that, but there we go. There. Can you all kind of see that parabola laying on the ground like that? And like I said, with time you get better at this, all right? It's not something that I just expect you pick up right away. And even mine's not that great, okay? So now my purple one goes down here, and then doesn't it go through the same 2 points? So when I draw that one, it comes like this, and then this side goes like that, let's just say. Good enough. So there are my curves laying on the ground. Now when I take this cross-section sliver, which I think I'll highlight this in red now. When I take this cross-section sliver, I'm perpendicular to the x-axis, right? Which means I'm parallel to the y-axis. So over here, if I'm parallel to the y-axis, I've got to be parallel to this, right? So my cut looks like that. There's my cut. And doesn't that form one of the sides of a square? That's what it says. My cross-section is supposed to come through here and form a square. So now, if I imagine going up the same distance and over the same distance and down, I would get my square. So notice how these two lines are parallel, and then these two lines are parallel. Those are vertical. Now that little cut that I took has a little thickness to it, doesn't it? I said I was going to come in here and cut this. And you see that I'm almost setting this up like a rectangle like we did in the past? I'm taking a little tiny sliver of this. So now what I want you to do is imagine this kind of drawn out here now. This thing has a little bit of thickness to it. Now I'm exaggerating that thickness, but that would be it, right? This little sliver that I cut, right, is just one small portion of the volume of the entire thing, right? But this is exactly like the same thing that we did when we had washers and shells. We try and find a formula for this object, and then we use the integral to add them up, right? That's the whole point of the integral, is to be able to add up an infinitely many of these of something, right? So can we come up with a formula for this volume of this little slab of that solid there? Do you know how long this is? Yeah, this is the top minus the bottom again, right? That's this length, and that's the top function minus the bottom function, right? So this distance from here to here for this particular problem is the top function, which was x squared minus 2, right? That's the top function. No, I just messed that up. It's the negative x squared plus 2 is the top function, minus the bottom function. The bottom function is x squared minus 2. Do you all agree with that? Now, why am I finding the length of this side? Yeah, I'm trying to find the area of this face right here. This face has an area to it, doesn't it? And then the thickness of it is like the height was when I drew that picture a second ago where it went like this or whatever, that thing. And I said, if we know the height, if we know that area, then the thickness of this, we just multiply the two. Well, I know that if I take this area and just move it to the side a little bit, that's going to give me thickness. So that's my height. It's just turned sideways. So the area of that should be this times this, right? Now, do we know what this is? Same thing. Why do we know it's the same thing? Because it's a square. I told you that, right? So this is going to be, let's simplify this now. This is going to be, this is 4 minus 2x squared. So if I distribute and clean up, get 4 minus 2x squared here. So that's what this is, 4 minus 2x squared. And then finally, how thick is it? Well, how thick is the slab? That's going to be the thickness of this, and I'm going to be doing these cuts left to right, a bunch of them, infinitely many, so that's going to be dx. And so the volume of this one little slab, the volume of this thing, is equal to this times this times this, right? So can I write it 4 minus 2x squared, that's this times this, and then times dx. That will give me the volume of that one little piece. Now what? You got to add them all up, right? That's just one little slab. So we got to add them up. That means we have to move that cut, that rectangle over there. We got to move it from left to right. And so here comes the integral. The volume of this solid that we're looking for should be, now do we need any pi or 2 pi here? No, because the formula for this little piece doesn't involve pi or 2 pi. So it's just going to be integral negative root 2 to root 2. And now the formula for the volume of that piece, which is that. That's it. There you go. If we could integrate that, we would have the volume of that solid.
So that first volume that's up there, that's specifically only
That's
the volume
just
from-
this one little cut. So you remember we had come up with a formula for the volume of a washer? We said once we had that formula, then we added them up using the integral. Then we came up with the formula for the shell. Once we had a general formula for the shell, we added them up with the integral. With this particular solid, we had to come up with a formula for one little piece, and then we need to add them up. Okay? So we want to look at the integral as being this tool that allows you to take anything that you can visualize and come up with a formula. It gives you the ability to add the things up. Yes?
Does the solid have an open bottom? Or is it like filled?
It's because it's a solid, it has to have a
So
solid.
It's just like, okay.
Yeah, it's
solid.
all the way through. So you could fill it with something. Well, you know what I'm saying, yes? Like if we took it and turned it over and it was like a shell, you would just pour in whatever it filled up, that would be your volume.
Yeah.
Yeah. Okay, good? Try part B. What's part B? Semicircles. So check this out. Our picture is going to be identical, except for this red thing is not going to be this red thing anymore, right? It's going to be something else. So let's just go through it. Let's take the time. Can I leave this picture here? I'm not going to redo this picture. Is that all right with you?
Sure.
Just going to redo the three-dimensional picture where we do our cross sections. So this is part B. We're doing semicircles. All right, so here we go to draw in three-dimensional space. Draw that, I draw this. Crap, missed it. There we go, here's X, here's Y. Now I realize that in physics, sometimes in physics classes, you draw three-dimensional space like this, and that's fine. It's the same picture, still follows the right-hand rule. There's just different ways to draw in 3D. Because you can always change your perspective, where you're actually looking at that from. This is, yeah, it's like a camera angle. A viewpoint, if you like. Yeah, it looks like I need to update. I haven't updated that in years. Okay, here we go. Draw your little parabola. And now I have a semicircle, right? So when I draw my little cut here, right there, right, it creates this little semicircle, a half circle. So if I blow that up over here, take a look at it, that will have a little thickness to it, just like it did before, right? Something like that. And we would like to know what? I mean, if we're going to do this, don't we still need to know the area of that face right here? And then the thickness is just going to be dx here again. So I need the area of that. So what is the area of half of a circle? So the area of this would be half of pi r squared, right? Half of pi r squared. Now, do we know what the radius of this is? Do we know what the distance from here to here is? Half of the what? Yeah, see, so the top to the bottom, that distance right there is the diameter. And the radius is always half your diameter, right? So this distance here, I shouldn't have put this here. I should have moved that somewhere else because it's going to get in my way. The area of that is equal to half pi r squared. That's what that is. But this distance from here to here, not from here to here, from here to here is half of the distance from here to here, which we already said was what? 4 minus 2x squared? Wasn't, when we did the square in the previous part A, the distance from here to here was 4 minus 2x squared. So if I take 4 minus 2x squared and I divide it by 2, that would be half of it, right? And it just so happens that this works out nice. This is just 2 minus x squared. Yes?
This one, it has symmetric, it's symmetric on both sides, on top and bottom of the dx axis.
It does.
So, but that's not always needed.
That's not always the case. I mean, this could be any curve up here. This could, so if I got rid of the symmetry, let's say I made this one come, let's say this one came down like this and did that, you could still do this, right? So your distance would be from here all the way down, and that wouldn't just be that distance, right? It would be, that distance, it would be whatever this is, top minus bottom, divided by 2. That's what you're asking, right? Yeah. So in this particular case, it's the top function minus the bottom function divided by 2. All right. So what is the volume of this then? What is the volume of that little slab right there? 1/2 pi, and then the radius, which was 2 minus x squared, squared. That would be the volume of that one little slice. Pardon? Oh yeah, the distance. Yes, I thought you said something else. And then that was the area, and then you have the thickness of it, the dx. I didn't label it here, but dx. All right, and then you want to add them all up, right? So we just throw the integral on that. So for part B, the answer would be 1/2 pi, which I could pull out of the integral, right? Because that's a constant. Then I would have integral goes from negative root 2 to root 2. And then I'd have 2 minus x squared dx. Make sense? Each one of these problems requires you to set it up and figure out the area. There's not like a general formula like for shells and washers. You just have to look at each one individually and come up with your little piece.
Since each one's going to give you a different volume, is there like a true volume?
Because it depends on what you want your solid to look like, right? I mean, there's no
Form of it?
no, because we're just creating three-dimensional objects out of this base. Like we're saying, this is the base. You could have an infinite number of different solids that have that base, right? Here's the volume of a few that have particular cross sections that look a certain way. All right, let's do part C. C is the hardest one. C is equilateral triangles, right? I think I'm going to get rid of this picture because I think you've got it. Don't think you need it for the rest of this. We'll see. We'll see for part C. All right, so for part C, equilateral